Okay.
Okay. So we left off yesterday in the middle of stationary black holes, and we derived that R0 over the norm of the Killing vector field for the stationary black hole should be constant on the world volume of the black hole. So that's where we ended. So today I'll, among other things, interpret this result as the zeroth law of black hole thermodynamics, as is advertised yesterday. But before getting there, we have to first write down what we really mean with this. I mean, to have a proper understanding, we have to write down some general class of how this Killing vector field could look. So, let's say we have some sort of background given by metric, and let's say this has a time translation Killing vector field. So this background could, for example, be Minkowski space, or it could also be ADS, for example, in some d dimensions. So we want a time translation Killing vector field, but we also want some rotational Killing vector fields. Of the background. And then we write a general ansatz for this Killing vector field as a linear combination of the Killing vector fields of the background. So this linear combination could then look like this, where these are constants, and they're constants, you know, over the whole space-time. So this is how it looks in the background space-time. Then, of course, we can take the pullback to the world volume. And in doing that, I will now assume that all of the Killing vector fields that I listed in this ansatz will also be Killing vector fields when I take the pullback to the world volume. One can cut this down a bit to only needing that there's one time-like Killing vector field and one like a linear combination of these. So one rotational Killing vector field that needs to be a Killing vector field in the world volume. So you can, if you want to sort of have the minimal set of assumptions, put it down to just having two of. But now I'll just you know, to make it easy for myself, I'll just assume that both the pullback of all S+1 Killing vector fields that I have here will also be Killing vector fields on the world volume of the black hole. So okay, so how do I write this? So I write that after I take the pullback of this, so in general, the pullback of a vector can be done in this way. Okay. So after I took the pullback of this one, time translation killing vector field, I'm going to write that on the word volume like this, where this TA is the unit, how to say, the normalized part of the killing vector field, and this will then be the norm of the word volume killing vector field, and it will be a constant. Yeah, one can generalize this a bit, but that is again a more refined story, so I will not go into that. Then we can do the same for the pullback of the rotational killing vector fields, so that will look like this. And then I've written them in terms of normalized killing vector fields on the word volume that is called CI. And again, RI are constant on the word volume. I will explain a little better, at least why this RI is constant in a little while. But then you see that now I can write my killing vector field, the pullback of my killing vector field K to the whole volume like this. So I'm just inserting what I just wrote in the pullback of this. And then you see that I can furthermore write this like this. Okay. And then I'm going to use this to interpret, if you remember, the velocity is equal to, first, let's compute the norm of this, that's what I want to do. So let's compute the norm. So k squared is equal to minus k squared, so to speak, and then we use these normalized norms here. So then you see that you get, so I can do this, minus, well, there's a r0 squared outside, then a minus 1 from this, right, and then a plus I from 1 to s, and then ri squared, omega I squared, or r0 squared. And then it's correct. Okay. So, and then I forgot a minus because I had a minus in front of the whole thing, right? So, suppose I define Vi as Ri omega I over R0. Then I can write this norm as R0 and then square root of 1 minus the sum over I from 1 to s, and then Vi squared. Okay. And then if we now look at the velocity, so the velocity was given like this in terms of the killing vector field. Then you see, then I use this and this here, right? So then you see that this becomes 1 over square root of 1 minus vi squared, and then ta plus sum from I from 1 to s, and then vi, and then zi. So this should remind you of something, namely the usual expression in special relativity for how you relate velocity in some direction to the relativistic velocity, right? So this is the relativistic d-dimensional velocity vector, but sort of what we call the physical velocity is really this vi, right? So in other words, this is the local velocity on the black hole. And you see now this k here is equal to some r0, which is related to a change in sort of my, it's a constant that comes in when I go from the time translation killing vector field that's natural to me in the background to the time translation killing vector field that is natural to me in the world volume. So this is a redshift factor in going from the background to the world volume. So this k here consists of the redshift factor and then some sort of, you can call it a boost factor. And if I now write up, if you remember, I had, if you go to a static frame and you sort of define everything so that you, you choose the local metric on the world volumes being in Cosby and everything. That's what I'm going to say. I mean, you go to a static frame on the world volume and then we derived that this was the temperature, or I told you at least that this was the temperature of the infinitely extended black P brane, right? When we didn't have this induced metric that could be non-trivial, and we didn't have any, we didn't look at the boosted black brane in that case, and so on. So what I'm going to tell you is then that if you now take into account that there is a redshift and it is a boosted black P brane, then this temperature will have both a redshift factor and a boost factor when you go to a frame where you include this, right? So the actual temperature will then rather be this, which is then, if we write it out, precisely this redshift factor thing. And you see now that this temperature, which take into account the redshift and the boost, is precisely constant because of this that we derived yesterday. So this is constant on the world this is the zero floor of black hole thermodynamics. Okay.
But this boils down to show that Ri is constant. R0 and Ri is constant.
I mean, I've already shown. Well, I'm not sure what you mean, but you know, I've already shown that this is constant. So I already know that the final expression here is constant. That is already that I already showed yesterday. This with Ri being constant, that I'm going to come to now because that is a consequence of. So if you have the embedding, if you look at what embeddings, say you just imagine you take d-dimensional Minkowski space, and then you want to make an embedding of a p-brane in that. Then I told you that we want to demand that the Killing vector field of the background, when it's then pulled back to the world volume, it should also be a Killing vector field. So the only way to accomplish this is if the what you call the orbit of the Killing vector field stays within the world volume of the black hole. I mean, it stays within the submanifold of the black hole. So if you for example think of the rotational Killing vector field, right? Then the orbit of this in flat space, right? That would be a circle in the rotation plane of the angle. And that means that if this should be a Killing vector field, not only of the background, but also of the world volume, you have to choose an embedding that lies on this circle. And then this Ri is simply the radius of this circle. So that's why these, I mean, it follows from saying that the pullback of this xi is a Killing vector field also on the world volume. It follows from that then Ri is a constant. Because that's the only way that that's possible. So in this sense, you can see that, I mean, if you demand that you have a stationary black hole, it's a very restrictive thing to demand. And you cannot just imagine any type of embedding.
So,
yeah.
Could you remind me what's the difference between black hole and black peeper? Because that formula is for.
Yeah. So I mean, it's sort of if you imagine you take some embedding, curved embedding or whatever, then the way I would want to say it is that, so you want to fold a black p-brane along this submanifold, right? So the black p-brane is sort of the local object that I'm folding, whereas the black fold is the whole thing altogether, the whole configuration of the global configuration that you have, whereas the black p-brane is more the local object that you are using to make the black hole.
But both have the same dimension, right? I mean, or
not
Yeah.
necessarily.
So the black fold. Yeah. I mean, the black fold is really. I mean, this is just what terminology is not. But so it's always like a p-dimensional, p plus one dimensional submanifold in d-dimensional space-time, right? That's a black fold. I mean, in part at least, because black fold is not only the submanifold, but it's also, the config. I mean, this part of the black fold is also the specific type of grain that you have folded, right? So that's also part of the black fold. But sure, it has the same dimension as the p grain you're folding. Always. So I have another remark which rests on this statement, namely that if you remember, we had two equations we need to solve to have a black hole configuration. But actually, the stationary black holes, this is already solved, and I'm not going to show it, but it's solved simply from demanding, that you have these demands on the Killing vector field K that I already described. That it's a Killing vector field of the background, it's a Killing vector field of the world volume, it's proportional to the velocity, plus that so demanding that those three demands, plus demanding that R0 over K is equal a constant, plus the specific putting in the specific energy, express tensor for the black P brane. So these specific epsilon and P that I wrote yesterday in terms of R0. That from those three things you can show that this is satisfied. So we are automatically, in some sense, satisfying the intrinsic equation. I mean, the conservation of the stress tensor is automatic once you have all this. So we only need to solve this equation for a stationary black hole. I mean, physically it makes sense because this equation has to do with whether, I mean, it's non-trivial if there would be some non-trivial forces pushing things around on the world volume. But here we are in an equilibrium configuration. So that is the only non-trivial equation we have to solve. So how do we solve this? So here will be a little bit sketchy, but so if we take this energy momentum tensor and plug in here, right? Then we can see we get epsilon plus P UA UB KAB mu plus P K mu equals 0, where this K mu is just defined as the trace of the extrinsic curvature tensor. Then you can insert the equation of state, so that P is equal to minus 1 over n plus 1 epsilon. So here we are really being very specific what type of black hole we're looking at. Then you can see, well, this gives you n over n plus 1 epsilon ua ub KAD mu equal to 1 over n plus 1 epsilon K mu. Then you can see that actually the epsilon you can just divide out, because it's on both sides, and also the n plus 1. So you get an equation like this. Okay. So this is another way to write the extrinsic equation. Then you can actually show this. I will not show, but you can show it that this thing here is something you can write as the transverse variation of the log of the norm of the Killing vector field. This is more intricate derivation, but it's in this Essentials of Black Holes paper, it's written there. This object here is just the projection orthogonal to the world volume. So you have the projector tangential, and you have the orthogonal. That's why it's written like that. So this sort of becomes make sure it's a derivative only along the orthogonal direction. And then I will skip even more steps, because it's just it's some complicated mathematics, and we don't have so much time. But it's again in this Essentials of Black Holes paper. Then you can actually show that this equation that I more or less claim is the same as the extrinsic equation. That in general, well, first you can see that this can also be written like this. This looks maybe strange at first, but this n here I can put in here like this. Okay, that I think you can agree with. Then how can I go from the norm of k to the n to minus p? Well, that's because p is proportional up to some constants to R0 to the n. And then we know that up to some other constants on the world volume, R0 is proportional to the norm of k. So this is proportional to the norm of k to the n. So instead of computing the variation of k to the n, I can just compute the variation of the pressure. And then I claim that there's a general result that once you have a formula like this, then that you can get from varying the following action. So if you vary this action, variations of this action gives this equation here, and hence also this equation here. So, so now we have sort of a prescription to solve stationary black holes. So what do we do? We start with background. So this is a prescription. We start with a background killing vector field. And this could, for example, be of the form that I described. I mean, you don't necessarily have to only consider rotational killing vector fields. It could also be a translational killing vector field. But here we just stay within. Here we only look at rotational killing vector fields. So you have this killing vector field of the background. This ansatz for the killing vector field, and then you find a general. So this is sort of step one. Maybe I have to write it like that. So step one is to write an ansatz for this, and then you find a general class of embeddings that are consistent with this killing vector field in the sense that you can also have that the pullback of the killing vector field on the wall volume is a killing vector field. And this specifically means, you know, that if you have a rotational killing vector field, then you have to be along a circle. So it will be more clear when I go to the example. So it means specifically that these are constant. R0 and R either. Then you also have to impose that T equal to, in this case, nk 4 pi R0 is constant. And then you have to solve extrinsic equations. And this you can do either by taking this, using this extrinsic curvature tensor and computing that, or you can use this axiom that I just wrote. So either way is fine. Most of the time the action is the most efficient thing. It should be a surprise. So before taking some examples, I just want to spend a few more minutes on this action because it's kind of it's related also to thermodynamics of the black hole. So if we look at the thermodynamics of stationary black holes, then first of all, we have to define what mass, angular momentum, and the total mass, the total angular momentum, and the total entropy is to talk about feminine. And to do this, we need this unit normal vector, because so you see that this is defined. I think I actually called that T before, so maybe I should use that. Well, it's always bad to introduce two names for the same object, but anyway, I called this T before, so now I call it N. Sorry for that. Then, why is this important? Because I have a, if the world volume, is a p plus one dimensional submanifold. So I can write that I would like to take out the spatial part of that, because when I want to, for example, integrate over and find the total mass, I don't want to integrate also over the time direction. I only want to integrate over the space directions, right? So the spatial part, which I call dp, since it's p-dimensional, is precisely the part which is orthogonal to this unit normal vector. That's also why I call it a normal vector. And then you can just write up what is the mass, the angular momenta, and that, yeah, I mean, I won't have time to go into details with why it's like this. Sorry for that, but I think at least you should in part recognize the formless. So you see the mass and the angular momentum are defined from the stress tensor, which of course makes sense. Here there's an important point that I didn't really spend so much time on, namely that the boosts along the world volume are gonna, seen from the background space-time, become angular momenta. Will become angular velocities, and hence there will be an angular momentum for each angular velocity. So in the examples that will hopefully be more clear. Then we also have the total entropy, which is defined using this entropy density that I wrote down. And then that can actually promote it to an entropy current, which is this part here. And then you have to, again, take the normal vector with respect to this. So all this you can find in the, if you want to understand this, you can look in these references. Okay. And this, I didn't tell you what this dVp volume factor is, but it's defined simply such that the volume factor that I used in the action is equal to the integral over the spatial part, and then this p-dimensional volume factor for the spatial part times R0, and then the integral over the time, which I write like this. So why go through all this? Well, because then you can look at you can get a relation between all these quantities and the action I wrote before. Because if you compute this contraction between the energy momentum tensor and this unit normal and the killing vector field, then you actually find, so here just write up what it is when we insert the form of, when we insert the form of the perfect fluid energy stress tensor, then you can see the contraction coming like this, and then we use this Euler-Gibbs-Duhem relation that this is equal to the local temperature times the entropy density, that epsilon plus p is equal to that. Okay. So this is T local times the entropy density. Then we have U dot n, and then we have U dot k. So U dot k, I can compute that is k squared over norm of k. So that is minus norm of k, right? So this is minus norm of k. And then n dot k, well, that picks out the special part of the killing vector field. Then you only have the norm of the special part of the killing vector field on the world volume. So this gives minus R0 from that. And then you can see that this is actually minus T times S times U dot N, and then minus R0 P. Because T local times K is so and if I now write out what this K is, then I have TAB NA and then psi B plus the sum from I from 1 to S omega I TAB N NA and then psi IB. Let me maybe put this. Okay, so that is this part here, and then I add this to the left hand side, so that will be plus TS U dot N. And this is equal to minus R0 P. And then this means that if you now compute this action I wrote before, and first write it in terms of the spatial integral, then you can now use this formula in place of R0P, and then you can see that you precisely get these three integrals, M, J, I, and S, apart from this delta T factor. So it becomes M minus the sum from I from 1 to S, omega I, Ji minus T times the total entropy. So I've related the action that gives me the extrinsic equation for the stationary black hole to the thermodynamic free energy. And if you go to Euclidean space, this will be even more precise, because then this minus delta T factor will become the inverse temperature . And then you actually get the usual relation between the Euclidean action and the free energy that you may or may not have seen holds for black holes in general. So that is a nice result, but it's also nice in the sense that it guarantees that any black hole that obey the extrinsic equation, I mean any stationary black hole that obey the extrinsic equation, automatically also obey the first law of thermodynamics and vice versa. And this is because if you take the variation of this expression here, then the omegas and the T are constant, so I don't vary over those. So I should only vary M, J, and S in terms of say, for example, the embedding that I have on the world volume to have a variation of these quantities. And doing that precisely gives me the first law of thermodynamics. So you know, if I vary this action, I know that I get the extrinsic equation, and if I vary that action, I know that I get the first law of thermodynamics. So it has to be equivalent. So it's not like we have to first solve all this and then afterwards ask, does it also obey the first law of thermodynamics? That is already guaranteed. Okay. Sorry if I went a bit quick over this, but yeah, I want to get through some examples also. So the first example that I will look at, we consider we want to bend a black string, so a black one brane, along a closed loop in d-dimensional flat space on the Minkowski space. So if we forget about the stationary case for a moment and just imagine doing this in general. So how can we do this? Well, let's write up the metric, some metric, suitable metric for flat space. So I want to put this closed loop in a plane, okay, just to not make things too challenging. So I want to put it in this plane, this closed loop. So then I should make some sort of embedding in that plane of some closed curve like this, where each point is then specified by the angle and then a radius, right? And then what should be my embedding? Well, first of all, so now we have two world coordinates. I'm going to call them tau and sigma. So my time, background time, I will choose the static gauge and set equal to the world volume time. And I will choose to parameterize the spatial part of the black hole using the angle, like this. And then the general curve is simply then some general function. It just means that the radius is some general function of the world volume time and the angle and sigma, which is equal to this angle. And then I should also specify that these xi's are equal to 0. So I choose to embed the black string in this plane. So one could then proceed to write down the full black hole equations for this. But we would like to find only the stationary black holes now. And the stationary case. And then we would like to write off what is the candidate killing vector field for the background. Well, that it should be pretty obvious that it's of this form, right? Because we're not involving all these other directions. Then you can ask, well, could we have a stationary, or in that case, actually static black hole with omega equals 0? That is obviously not possible because this string has a tension and it will collapse. So it cannot be time independent if omega is 0. So we have to turn on omega, and that means that that both of these should be both of these killing vector fields should be killing vector fields on the world volume, and that is actually something guaranteed by the rigidity theorem. So before I just said I'll just assume it's like that, but the rigidity theorem in general actually gives me that there's at least one rotational killing vector field, and since this is the only one I invoked, that really has to be there on the black hole. So this has to the pullback of that to the world volume has to be a killing vector field, and that also means that the embedding of the black hole has to lie along the orbits of this killing vector field, and the only embedding that can do that is a geometrically round circle. So I get that demanding stationarity already without solving any equations gives me that the only possible embeddings of a closed loop are circles. So then I should modify this ansatz to take that into account. So the two first are still there, but the third one should be now a constant radius. So like this, right? And then, so then you see, so I did this part I did this part. Then I have to impose that the temperature is constant and solve the extrinsic equations. Right? So let me look at the induced metric. So this is just the following. Shouldn't be very difficult to see. And then you can compute the square root of the minus the determinant. This is equal to the radius. So if you now take this killing vector field of the background and put it on the world volume, then you can see that it's actually nothing but this killing vector field here. Then we should look at these normalized killing vector fields. So we should find the norm of this. But then you see that is given here. So this Ri, in this case, that only one R, and that is the R is then equal to the R that I defined here. That's why I chose that notation, of course. So this velocity that I had before is just R times omega. And that, of course, makes sense because because physically the velocity on a small part here is precisely the angular velocity times the radius. Right? So it makes sense that the physical velocity locally on the black hole is this. And that means that this norm of the killing vector field I can just now compute as 1 minus v squared or 1 minus r squared omega squared. And you notice there's no redshift factor here, but that's because I chose the background to be flat spacetime. So this R0 is just equal to 1. So then that gives me the equations necessary to impose that the temperature is constant on the black hole. Then I have to do one last thing, which is to solve the extrinsic equations, and then I'm writing too big. So I try to do it here. I think this perhaps.
Sorry, what should be R0 in this case?
Yeah, so R0 in this case is just 1. Because when you.
Okay, that's the redshift. So
so because you see here there's just minus d tau squared.
But it's the same R0 lower that appears in
This R0.
Yeah.
No, that's another R0. That's the local horizon radius of the black pea brain. So if you zoom in, let me get back to that. I hopefully remember. Otherwise, remind me because that I can illustrate in a second. What that is. Okay, so yes. So let me write up what the temperature is. So this is the temperature from my computation of this normal killing vector. So this means that the little r0, which is the Schwarzschild ratios of the black grain, is equal to this. Okay? And this means that I can now compute the pressure in terms of this. So the pressure was given by this. And then I insert what I found R0 to be. Like this. And then, if you remember it's here, the pressure gives me then the action. So I can write out the action. So the action then is minus this omega n plus 1 over 16 pi g n over 4 pi t to the n integral over the world volume, so d tau to sigma. And then I should remember this square root of minus gamma, which is r. And then I have this vector here, right? So this becomes my action. And then when you vary this action, you should only vary, you should basically only vary over the embedding of the black ball. And the only variable in this embedding is this radius, r. So to find the extrinsic equation from this action, I should just vary over r. Okay? So the action principle tells me that this variation with respect to r should be 0. And this is then, first you have delta r from there, right? So then it's minus r squared omega squared. Then you should vary this part here. So that is then n halves, and then 1 minus r squared omega squared, n halves minus 1. Then you should differentiate the thing inside. So that is minus omega squared 2r delta r. So then you can see that this is equivalent to, you can divide out with the delta r, of course, and you can also take out this factor here, and then you get, so if you take out this factor here where there's a minus 1, you get a 1 minus r squared omega squared from over here. And then you have, the 1 half goes out with the 2, so there's a factor of n, and then r squared omega squared. So in other words, you get that 1 is equal to n plus 1 r squared omega squared. So r has to be equal to 1 over square root of n plus 1 times 1 over omega. So you see now that we solved, we did the whole procedure now. So now we really found a stationary black hole. we solve all the equations and put all the conditions and so on. So this is really a stationary black fold that this corresponds to. What is this black fold? Well, this is nothing but a rotating black ring. So if we try to picture it on this plane again, it's just a ring that rotates, and it has a specific radius, and the radius and the angular velocity of the rotation are related to each other in this specific way. So it's a rotating black ring. And if you look very close to this, so if you sort of imagine taking a very small piece of this ring and zooming in, you would see that this is really a black string with the horizon radius R0 and so on. So it has an event horizon, etc. if you zoom in locally. But if you sort of zoom out again, then it looks like an infinitely thin string with the stress tensor, blah blah blah. And you can see that it's a rotating object. And this is I'm sort of rewriting history a bit here because I never told you about what possible other exact solutions you have in higher dimensional gravity, higher than 4, right? Apart from the Schwarzschild-Tangolini black hole and the Myers-Berry black hole. But there's one other exact solution, maybe you all know this, I don't know, but there's in 5 dimensions, there's the exact solution for a rotating black ring. Found by Pietro Antonio and you can then show that the limit where the horizon radius is much smaller than the radius of the ring, this exact solution precisely becomes this black fold. But we can also turn this around, sort of to take the black fold point of view and say that if these guys hadn't found this solution, we would have predicted that it was there, right? And in fact, they only found it in 5 dimensions, but we predict that there's such a solution in all higher dimensions, not only 5, but 6, 7, etc. And so another remark surrounding this is, of course, that this illustrates my statement that there's many more types of black holes than just the Myers-Berry black hole, which is the equivalent of the Kerr, and the Schwarzschild-Tangolini black hole, which is the equivalent of the Schwarzschild black hole. So in high dimensions, there's many more types of black holes, and you see here that this is a black hole with a totally different type of horizon topology, because this has the horizon topology S1 cross S E-3. The S1 from the circle and the S3 from the local sphere on the black string. So you not only have the spherical topology that you're used to from dimensions, but you have other topologies as well. And then, since this works so fine, and we find this new solution and all that, one could ask, can you find more solutions than this that are not already found as exact solutions, at least in special dimensions? Before doing that, I just want to mention one more thing with the black ring, which is quite important, which is, why is there this relation between the radius and the angular velocity? That's because if you want to have such an object and it has to be stationary, so there shouldn't be any time dependence, then you need to balance the forces to attain equilibrium. And what are the forces here? Well, there's the force of tension, which tries to pull the brain together, like an elastic band, right? And then, because we have a rotation, then there's oppositely a centrifugal force. So, for this omega, given a radius, this omega that you have determined here is precisely the angular velocity where you have a balance of these two forces. And that is why you can find it as a stationary solution. So I don't know, is it okay if I don't take a break today, or are you mortified? Just because then I can get a little further. Okay, no protests. So I'll quickly go on and okay, maybe I shouldn't have deleted this, but anyway, hopefully I remember. So then I want to talk about other examples. Sorry. Yeah.
Are the solutions stable against perturbation?
This is not stable against perturbation, no. So, for one thing, you may know that there's a regular Flaming stability of the black string, so that will already kill it. Then also, the embedding itself, if I remember correctly, is also unstable. So, but even if it's unstable, it's an unstable equilibrium, right? So you can then hope that once you go to the limit where it's not thin anymore, but more fat, so to speak, that it then can find a stable situation. And I think also, I'm not sure this has really been studied. For some reason, this hasn't really been studied as far as I know. If you take other brains than just the black string, I mean, for sure you can have that the regular Flaming stability disappears. That I will try to reach in the end. And I think it's possible you can also find a brain for which the embedding is stable. I don't think people really start from that last part. So then we go to the example 2, which is something called odd spheres that I will try to find. Because what you will see now is that this rotating black ring is actually just a little part of a much larger family of solutions. So what I would like to do is to instead of taking a black string, I want to take a black P equal 2 plus 1, 2k plus 1, I mean, just to get an odd number, frame, and fold it or bend it if you want. Along a geometrically round sphere. And the reason it's called an odd sphere is that it's only odd dimensions you can do this. So you can then write up, how should I do this? Well, I write up again, I want to do this in flat space, in d-dimensional flat space, so I can write up some appropriate coordinates in flat space. This, where I parameterize my angles in a special way, namely, so I have k plus 1 rotation angles, phi I, and those are the rotation angles of the k plus 1 planes, because the sphere is embedded in R2k plus 2, so that's k plus 1 planes, and those k plus 1 rotation angles are the k plus 1, correspond to the k plus 1 planes that you have. And then there's some other angles as well, which I've specified which you specify in this way, and it's like you can see that there's actually one variable too much if you look at the total number of variables here, but that's because you have a constraint that you have to obey on these variables here, ui, which is that this has to be equal to 1, and this is a standard way to parameterize, and it's called these variables are called director cosines. Then we are looking for the Killing vector field of this form with these k plus 1 rotation angles. And then we can write down embedding corresponding to this, but I'm gonna skip some steps here and like I wrote here, just impose that it's geometrically round object, and related to that, I'm gonna assume that all of these angular velocities are equal. So you just get a single angular velocity for all of these rotation angles. Then my embedding will simply be, so T is tau or sigma 0. And then I say the rotation angles are the k plus 1 first directions. So I from 1 to k plus 1, because there's k plus 1 rotation angles. And then these mu I will choose as the rest of the coordinates, with the one note that I only choose k out of the k plus 1 directed cosines because of this constraint. So altogether, this gives me the 2k plus 2 world volume coordinates. I mean, including the time, it's 2 place k plus 2. But this is only this doesn't really specify so much the embedding, because for that I also have to specify what this radial coordinate here is. So the radial coordinate, I choose that so that it's a geometrically round sphere, which means it's just a constant radius. You can generalize this a little bit, because it could in principle depend on all these directed cosines. It cannot depend on the rotation angles because then it's not a stationary vector. But it could depend on directed cosines. And it might be that then one can find spheres that are not geometrically round. But nobody found them yet. Okay. So now we stick to geometrically round spheres. Then we can look at the induced metric and all that. So this works exactly like for the black ring. So here in this form of the induced metric, I'm gonna write in terms of the mu's and the other variables of the. Since I anyway identified these variables, I can write it in terms of the space-time variables rather than these omegas, since I think the form is more clear. So this is the induced metric. Then the square root of the induced metric is of the determinant of the induced metric times the integration element. You can then see this gives me the radius 2k plus 1 times, and then we have the integrals over the time, and then the integral over all the angles. But this is nothing but a unit k plus 2k plus 1 sphere, so you just get the volume element of 2k plus 1 sphere. Then we can also compute the norm of k on the work volume. And here you need to understand what are these RIs that I talked about before. So if you take this killing vector field, one of these rotational killing vector fields, and look at what norm does it give on the world volume that you can read off from here. That is precisely the R squared factor times the directed cosine factor squared, right? So this gives that Ri is mu I times R. So this is 1 minus sum from 1 to k plus 1 mu I squared R squared. But then the sum, sorry. Yeah, omega, sorry, yeah, thanks. That's omega as well. And since they're all equal, it's just a common factor. Then this sum here is just equal to 1 from this constraint. And you get then that the norm of the killing vector field is 1 minus R squared omega squared. Okay. So if you again go through finding the temperature and the pressure, it works exactly like before, and then write up the action. All that changes in this case is that the action will now, up to a constant that I don't have to vary over, the action will now be the integral over r to the p times 1 minus omega r squared omega squared n halves, and p, because p is 2k plus 1, so this is equal to rp. So this rp comes from the square root of minus the determinant, and this comes from the pressure. Okay. So if I want to find a stationary configuration, I just have to make this variation. This is exactly like before, so I just have to make this variation. And then you can solve this equation. Yeah.
Just as before, when r is 0, we have just k of 1 is on this program. But on the right side,
So when r
should
is
be infinity and
sorry, but I'm not sure I follow you.
this r, big R,
Yes.
if it's 0,
Yes.
then the k is just 1. This norm of k.
Yeah.
At the end, if r is 0, it means omega is infinity.
Sure.
And then we have 0 times infinity. But we know that it should be 1.
Yeah, but there's several steps where what you say sort of goes wrong. One step is the most obvious one is that the embedding you're trying to make has infinite curvature. So it completely violates the black hole approximation, because you're basically trying to take some p-dimensional black hole and shrink and put on a point. Because if I is equal to 0, it's a point in the background space. So it's completely singular embedding that you're trying to make. So I'm not surprised if something goes wrong in this case, because it's not supposed to work in this case. But anyway, so this is the equilibrium condition, and this is completely analog of the black string. But now what we did was to take a black P-brane and fold it on a p-sphere, and for example, so you could, for example, take, say, in 10 dimensions, then you could take a black 3-grain on S3, right? And then you would get an object which has S3 cross S5 topology. And if you remember, I don't have time to go through that, but if you remember, I also gave you specified what the energy momentum tensor for the black DP brains, so charged brains instead of neutral brains. And you can go through all of this, and then you find a slightly more complicated formula for the radius here in terms of the angular velocity that also involves the charge. And then you can also take, say, a black D3 brain and fold it or wrap it on a S3 in string theory. So you find new, you can find new configurations in string theory also in this sense. It's not just, I mean, I've stuck to pure Einstein gravity most of the way, but you can generalize all this to supergravity and include charged brains and so on. And then you would think that we would be quite happy with this already, because this is a much more general family, but there's an even more general family, of course. And I will not go through the derivation, I'll just say what they are. So instead of making a single odd sphere, you could imagine taking a product of odd spheres. And then that would give you a P equal P1 plus P2 plus PL dimensional spatial submanifold. So you should wrap a black P brain, for example, on this, where P is given by this. And all of these has to be odd. You cannot use an even sphere because an even sphere has what is it called? I mean, you cannot support you cannot support an equilibrium condition like on the, for example, on the North Pole or on a 2 sphere. There you have to you cannot have an equilibrium condition there. So even spheres are not possible. So this is all products of odd spheres.
This relates to that we cannot use vector field on sphere.
That you cannot what?
I mean, it has area characteristics not equal to 0, so you cannot use vector fields on the sphere. It relates to that, or
I think so. Yeah, I think so. Yeah, there's a. Yeah, I mean, at some point, some years ago, I was talking with some mathematical physicists of trying to prove it in that sense, but we never got around to do it. So but I would suspect so. So what is the event horizon topology? Well, you just have to multiply with you just have to multiply with the with the event horizon topology you have locally on the p-plane. And then you can write a list of all the possible high-dimensional. I mean, it's an infinite list because you have an infinite amount of dimensions. But just to illustrate this a little bit, we can look at what possible objects you have in high dimensions in the first few cases. So say in 4 dimensions, we know there's only S2. In 5 dimensions, we have S3 and S2 cross S1. In 6 dimensions, S4. So this is the rotating black string where we found an exact solution. Right? Then you can have a rotating black string also in 6 dimensions. It will have this horizon topology. I mean, this is just a Myers Perry or Schwarzschild-Tagliani black hole. But then in 6 dimensions, you can use this product construction to have a torus. So T2 cross S2, because a torus is just the product of 2 circles. So then in 7 dimensions, you get the Myers Perry black hole, you get the black ring. Then you get again the torus. And then you get, say, a 3 sphere and a 3 torus. And so on. So if I should list I don't know if it's worth using time. But I get in 10 dimensions, for example, if I can do it. You get really quite a lot of possibilities. It's a really long list. Let me just do like this. I mean, there's let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 16 types altogether, as far as I can count. So you see that suddenly you have expanded the amount of black holes you have enormously. And this is, of course, related to the challenge. It's not the only reason why it's hard to find uniqueness variants, but it's of course related to this as well, that you have really a lot of different types of black holes. So if you wanted to write down a uniqueness variant, you should beyond specifying the mass and the angular momentum, you should specify some further invariants that can distinguish all these cases. Then you could say, well, couldn't this further invariant just be the topology? But actually already in 5 dimensions you can see that that the black ring here is not specified by the mass and angular momentum alone. You have to specify one more quantity. So it's not enough just to say that we add the topology of the object. So questions to this?
D was 10, geometry S1 course S8 is now D minus 3. Is that horizon geometry?
This one?
Yeah, the second vector is that D minus 3?
Ah, sorry, you're right. Actually, I was writing D equal 11. Sorry. Yeah. Yeah. So to D equal 10. Yeah, sorry for that. Then I can tell you how many there are in 10 dimensions. If you really, I don't know if you care, but there's 1, 2, 3, 4, 5, 6. So in 10 dimensions, there's 11. Yeah, sorry. Thanks for that. We haven't tried to study how the number grows with the dimensions. So I don't know how it grows. So more questions to this. Yeah.
I wonder, just this is curiosity. Yeah. So with this kind of metrics, solutions, if you replace, for instance, in this Gauss-Codazzi equation, they should explode, right? Because these are like singular objects in less dimensions. So if you write the induced curvatures in this sense, they should give you infinites. I don't know.
Infinite what? Sorry?
This Gauss-Codazzi equation.
Yes, yes.
Because in this sense, these are black brains. They are black holes embedded in some way. So
Yeah.
if you replace those solutions in those equations, they should.
No, it's sure. Yeah. So yeah, that's. Here I've been very restrictive, but you can. There's an even larger space of possibilities. You can take any type of charged black hole. You can take any, your favorite type of black hole, and then you can add p-dimensional Euclidean space to make it into a p-brane if it's not already a p-brane, and then use this method. You can add rotation, local rotation, because I started with my black p-brane being the analog of the Schwarzschild black hole. The Schwarzschild black hole times r to the p factor, p-dimensional Euclidean space. But I could also start with something like the Kerr black hole or the Myers-Perry black hole, and have local, intrinsic rotation in the black hole. That gives me also, so it's really, in finding this enormous amount of possibilities, I've been quite restrictive. So if you sort of open the floodgates of all the black holes you can think of, then you can, it's really so many new black holes that it doesn't really make sense to list them anymore, I would say. Okay, so more questions to stationary black holes. I hope I've been a bit quick today, but I hope you at least have some rough understanding of how this is constructed. And, it's all constructed in this particular regime where the scale of the embedding or the background metric is much larger than the size, the thickness of the black P-frame. So, of course, this you can say is a limitation, but this is precisely the feature that makes it possible to find all these solutions. So, it's because you have this regime where you have largely separated scales on the event horizon that you are allowed to write down an effective theory for black folds that, or black holes, you can say, where you can describe all this. And then in 4 dimensions, this is not possible. You cannot find, to our knowledge at least, examples where you have largely separated scales in the event horizon in 4 dimensions. And also you don't really find extended objects like these black P-frames, because, say, if you wanted to have a black string in 4 dimensions, you would have to use a 3-dimensional black hole, and at least without putting a cosmological constant, 3-dimensional black holes don't make sense. So for that reason, for those 2 reasons, this is something new in higher dimensions, in higher than 4 dimensions, and this is you know, the reason why you get so many more solutions in higher dimensions. Okay, so before, as the last thing, I want to briefly talk about a non-stationary case, because this black hole technique can also be used for non-stationary configurations, and you can in general study the perturbations, but suppose, but now I want to consider a very specific type of perturbations, where the wavelength, so this is the wavelength of the perturbation, and then I want to study the regime in which this wavelength is much smaller than the scale of the background and the scale of the embedding, but much larger than the thickness scale of the black fold, which would be, for the neutral black P-brane, would be this R0. Okay? So in this regime, because this wavelength is much larger than R0, I can use the black hole method to describe these perturbations. But on the other hand, since it's much smaller than the scale over which the black hole varies, I can ignore that the embedding might be non-trivial, or that the background spacetime is non-trivial. So I can just study these perturbations, assuming that the embedding is completely flat and that we are in Minkowski spacetime. So this embedding here will just be sigma mu from mu going to from 0 to p, and then 0 otherwise. And the background spacetime, I mean, this can just be a local Lorentz frame if you actually have a more complicated black fold. And then this is just a local statement, or you could imagine that it really is a straight black brane in Minkowski space. So then we want to study the black-fold equations. So we want to study these two equations. So now both of them are going to be non-trivial because we are not in the stationary case anymore. Then in the unperturbed case, we assume we have some constant energy, density, and pressure, and we also assume that. So this is something that doesn't follow from all of this in general, but here we just assume it for simplicity. So we assume, this could follow from that or whatever, but that the velocity is that you're in a static frame. That might not be natural locally on the black fold. But here we just assume it, so that we are in the static frame. Then we want to perturb all this, and we also want to perturb the black fold. So we want to make a perturbation of the energy density. We want to make a perturbation of the pressure, and we will write this in terms of the variation of the perturbation of the energy density like this. And then we want to have a perturbation of the fluid velocity. So to first order, that will look like this, where I is from 1 to p. And then you can also imagine perturbations of the embedding, which is this, where the unperturbed embedding is this trivial embedding here. And with abuse of notation, I'm going to write these perturbations of the embedding as psi m, where m are all the transverse directions. So from p plus 1 to p minus 1. Because of course only the transverse perturbations are physical. Then you can find the perturbed stress tensor. So from epsilon plus p, you get this factor here. Then there's the perturbation of the fluid velocity. Then there's the perturbation of the pressure times the metric. And one can check that to first order, the world volume metric is not perturbed. So if you look a little bit at this, you can see that the individual components of the stress tensor can be written like this. So that's all we need for studying the intrinsic equation here, right? And since the world volume metric is just the Minkowski metric, this covariant derivative is just the usual derivative. So let's try to write down the intrinsic equations. can see that if you take b to be 0, then you get 0 equal d0, 0, 0 plus di gi 0. Or if you took b to be spectral, what I call I here, then you get so 0I plus j tj I. And now you can then combine these two by looking at the second derivative with respect to time of t0, 0. Then you can use this equation here to see that this is this, right? And then you can use this equation here, that this is equal to minus that, and then you see that this is di dj dij. Very strange thing here going on, but then I might have some sign problem here. But anyway, so if we insert, if we now insert a specific case, so this specific energy momentum tensor, then up to the correct equation you should find should be this one. And this thing here is a constant. So this is nothing but a wave equation for this delta, the perturbation of the energy density. So since it's a wave equation, we can solve it as the following: some amplitude e to the minus I omega tau, e to the I ki, and then the volume directions. And then you can see that if this should be, you can put this in here in the equation, and then you can see if this should be a solution, you're required to have that omega squared plus dp d epsilon k squared, and here k has nothing to do with the killing vector field because we don't have any killing vector field here. So k squared is just this ki sum from 1 to p. So k is the, I think you call it the wave number. Yeah, k is the wave number, and omega is the frequency of this wave. Right? So you have this condition, and then we just have to, then we can just take an example. So, because I've been fairly general here. So what is the, let's take an example. So for a neutral black brane, this is true, then dp d epsilon is minus 1 over n plus 1, right? So you see from way down there that then omega squared over k squared has to be equal to, I think I must have some. I think I may have a sign problem here. I don't have time to fix it. But the point should be that this should be negative, because then it means that, so if this is negative, which it indeed is, then this also has to be negative. So I guess this has to be the right sign, and then I just made a mistake somewhere over there. So since this is negative, then omega squared is negative, and that means that you have an instability. Because then if you take, then omega is imaginary, and then this can give you a growing wave, a mode of growing time. Right? So what is this instability? Well, this is nothing but the long wavelength limit of the Gregory-Laflamme instability. So here we derived the Gregory-Laflamme instability just using this fluid approximation to black pea brains. And you can even see that if you say that omega, say, is I times some real big omega, then you get that omega is 1 over square root of n plus 1 k. And this is actually the limit of the dispersion relation of the Gregory-Laflamme. I don't know if you know this, but the Gregory-Laflamme instability has a dispersion relation like this. And then, if we want to take the long wavelength limit, we have to set k to 0. That's the long wavelength limit. So what we are computing is this tangent here. And if any of you have tried to look at the Gregory-Laflamme differential equations, they are horribly complicated differential equations. It's something like, where you have to use more than a page in LaTeX to write it down, maybe even more. But here we find it, a limit of it pretty easily. There's many more things to say about that that I don't have time to say. Like you can also find the second order correction and then see that it curves the right way. This comes from dissipative corrections to the energy momentum tensor. Then you can also study you can insert the energy momentum tensor for a black pea brain that I actually wrote in an earlier lecture. You can just insert that here and see you can compute dp dE for a fixed charge, and then you can see when can this be positive, and then you get a constraint. Just gonna write the result. That this has to be bigger than n minus 2. And this was related, this alpha was related to the charge. So it means that if we are sort of suitably close to extremality of the black pea brain, like say if the temperature is low enough for a given charge, then the Gregory-Laflamme instability disappears. And this is actually something Gregory-Laflamme already computed, but again using these enormously complicated differential equations, and they didn't solve anything analytically. They just they could just find a miracle. Like they could find, like a point here, a point here, and a point here, and a point here, and so on. And then see when does this look like it's going to disappear. But here we can derive this condition for the absence of the instability analytically. in a very easy way. Then I didn't have time to look at the extrinsic perturbations, the ones that is actually easier than the intrinsic ones. And what you find is that if you have a positive tension or equivalently a negative pressure, then the brain is stable under extrinsic perturbations. Of course, then this is only at scales smaller than the embedding scale. So if you go at larger distances, this might not hold. But say if you have a brain which is lying completely flat in Minkowski spacetime, then the extrinsic perturbations are not are stable, or the brain is stable to extrinsic perturbations. Okay, so I think since I'm out of time, well, so if there's more questions to anything, otherwise I will end here. Thanks.